In the first video of this series, entitled All of the Ebow Schematics You've Seen Are Wrong, I discovered that all of the Ebow schematics on the internet are wrong, and I theorized about how the circuit may work. The second video was to correct a few errors that I made in the first one. In Ebow Resurrection Attempt Part 1, I reassembled a completely destroyed unit that I obtained from someone after their unfruitful attempt at uncovering its secrets. I had to rewind both the driver and input coils, guessing at what the actual target was. In Ebow Resurrection Part 2, I created a testing jig, tried different spice simulations of the circuit, and ended up with a unit that didn't work. I thought that was the end of the road, but because I felt like the goal was still in reach, I decided to revisit the project. In Ebow Resurrection Attempt Part 3, I did some more rewinding of the output coil, performed experiments, and did some testing, and more testing until I found a combination that worked. While in the end it wasn't 100% usable due to a low output, it did functionally work exactly the same way as my fully functional untouched Ebow. In this final episode, I will build the internet Ebow to see if it actually works, share some LTSpice simulations that are very close to what I observed in real-world testing, and I will attempt to tackle a couple of remaining mysteries. Here's that Ebow internet schematic that I've shown in previous videos is incorrect. I've hand drawn it up here, and this differs from the actual Ebow in a few different ways. The actual Ebow does not have a bypass cap on pin 7. There's no Zobel network. The 1N4148 is actually doing something completely different than circuit protection, and there is no feedback loop on this internet Ebow schematic. Now, I discovered that several years ago, I guess I had started to create a Ebow circuit based on this internet schematic, and I had created this circuit board that I had never really finished, and this morning it only had the LM386, the resistor for the LED, and these two capacitors on it. And I have since added, I had to drill some holes, I had to add the bypass capacitor and the Zobel network to it, and drill some holes for the input and output coils, which I wasn't quite sure when I created this. This is a long time ago, but I'm pretty sure I wasn't sure how to do the input and output coils. So having had to rewind the input and output coils on my Ebow Resurrection project, I came up with this idea this morning. And this is simply just a couple of screws that I'm going to screw into the circuit board. So they'll just screw in there when I'm all done, and I'm going to have to rewind or wind some coils here. And so these are just basically little round pieces of cardboard that I have fashioned into a bobbin. And I had to create a way to have these attached to my hand winding jigs. So what I came up with is a little attachment here that will allow me to screw in the bobbin like so. Then I'll just be able to wind it like so. And when I'm done, I'm going to stick these little rare earth magnets on the end here where they screw through the PCB, and this will become basically my pole piece. These little rare earth magnets that I got at Radio Shack, like, I don't know, probably 15 years ago, are as strong as the little half-inch round button magnets in the real Ebow. So I'm thinking this should work. I guess we'll find out. And so for the wire, what I'm going to do is use the same wire I used on the output coil for the Ebow Resurrection project, which is just some little transformer that I'm not even sure what it was exactly, but I used the wire from this. So the object is to get 8 ohms of wire onto the output coil, which is going to be the red one, and then I need to get about 100 ohms of wire onto the input coil, which is going to be the blue one, using wire I've left over from this dissected Mouser 42 TM018 audio transformer. I should have enough to get 100 ohms on here, and so apparently the secret formula to this circuit allegedly working is I need to have 100 ohms of wire on the input coil and 8 ohms of resistance on the driver coil. I keep calling it output coil, driver coil, it's the same thing. So that's what I'm going to do next, is wind some wire on these little bobbins, and when I get to the required specs I will pop them onto the circuit board and solder them onto the PCB, and then basically I'm ready to test. This is quite a simple little circuit here. Since there's no feedback loop and oscillator frequency and all this other stuff that I have to be concerned with, this should be a very simple project. And we'll find out if it actually works or not. Here I have the circuit basically all done. I've wound the coils. The input coil is the one here on the right side, and I ended up using a little thicker wire than what I originally thought because I just didn't have enough of that really thin wire. And so I have about almost 100 ohms on here, and then the output coil has 8 ohms of wire on it. It's basically the same gauge as what's on the input coil, and as you can see there's barely any wire on there to make it 8 ohms. And so when you actually use this thing, the screw here on the driver coil gets kind of warm, and so does the LM386, and it's not really acting like an Ebow. I will demonstrate that here. Get that plugged in. Okay, we'll turn on our little audio amp. So we have a nice little oscillator. It's running at about 2.5 kilohertz, and it's not doing anything to excite the string. Try switching the magnets around, see if that does anything. I can hear it trying to do something to the string a little bit. It won't do anything to assume the frequency of the string, however. I just don't think the 8 ohms on the output coil is enough, so I'm going to just go ahead and quadruple it to 32 ohms and see what happens. And at that point, I'm just going to stop. I rewound the output coil. I just started over actually instead of adding wire this time, and I have about 32, 33 ohms on there. And so then when I powered it up again, I found that now I was having the input coil getting a little warm and the LM386 getting really hot very quickly. So I just did a little hack and added a 470 ohm resistor in series with it. So the total DC resistance on the input coil ends up being now about 556 ohms. And the driver coil now has about 32 ohms of DC resistance, and now it self-oscillates at 1.95 kilohertz. So let's see what it sounds like now. A nice oscillator once again. It will actually drive the string into vibrating, but it's not anything related to the fundamental of the open E string here. It will eventually lock onto a note that I fret. You can see it's not very usable as an Ebow, is it? It really only works over the bridge pickup too, so do-it-yourself Ebow? I don't know, I don't think so. Once again, this is using the schematic on the internet that I've shown in previous videos is incorrect. I know someone's going to ask, what about that Russian guy that made a working do-it-yourself Ebow? Yes, it does work and it seems to work well. However, here are some observations. I have no idea what he's using for the input and driver coils, but they look like they just barely do the job, which is probably why the coils have to extend through the bottom of his 3D printed housing. If you watch carefully, you'll see that the circuit board has a feedback capacitor and resistor, the 10 microfarad bypass cap, and there is no Zobel network. It appears that he has made a do-it-yourself version of the Ebow that predates the Plus Ebow, which did not have a harmonic mode. So it is possible to create a worker-like circuit, but the key to it working or not is those coils. They need to have the right specs or it won't work properly otherwise. In this simple animation, we can see the relationships between the fundamental frequency of a vibrating string, which is fixed at both ends, and its second and third harmonics. I calculated where the antinodes would occur on a guitar with a 25.5-inch scale. Here's where the antinodes occur at the fundamental, second harmonic, and third harmonic frequencies. The second and third harmonics fall into the area where the guitar pickups are normally placed, 1 to 7 inches from where the strings sit on the saddles. The Ebow is typically used in the area where the second and third harmonic antinodes occur, so the Ebow in part simply takes advantage of string wave physics. Once the string is excited into vigorously vibrating by the Ebow circuit, it either doubles or triples the fundamental frequency of the guitar string, and then all it has to do is maintain it. In the previous videos, we learned that its operating frequency is approximately 2.4 or 2.6 kilohertz, depending on how you set the mode switch, and that it is in standby mode until you place a metal object between the coils, which causes it to wake up, so to speak. So the question then is, why are these two frequencies used? It appears that the reason why the 2.4 or 2.6 kilohertz scheme was chosen for the oscillator frequency is because At 2.5 kilohertz, there is a gain boost, and it makes sense that the two modes would be centered around that. It would be desirable to have maximum strength available when you engage the circuit. We'll see that in the next section of this video. Someone suggested that I build this arrangement to test the round-trip gain and see if we could learn anything about the phase of the signal coming into the Ebow. And what it consists of is building a little coil here, and we would feed it a signal from a function generator and put that under the input or sensing coil, if you will, and then we would see what happens at the driver coil through a guitar pickup connected to an oscilloscope. And so I started making this. I made this coil, which is essentially a snooping coil, which I can use for other things, but I realized that this doesn't really work because the Ebow won't do anything unless there's a guitar string between these two coils. So I had to come up with a different way of trying to find out this information. So I built this snooping coil, and essentially it's wire that I pulled out of an old wall wart that I had to hack apart to get to the wires, and it's got a 0.4 millimeter wire. And I wound 20 turns around like a 20 millimeter around or so socket, and then I put a 100 ohms resistor in series with one of the legs, which is I made that the positive, and I used a little plastic tube for a handle, and this gets connected to a BNC jack and ends up looking like this. And so here's my windings from the repurposed wall wart, the plastic tube, and my 100 ohm resistor right here. And I added these couple pieces of plastic tubing to the wires so I could extend the length of it, and I also needed to have it be rigid enough to where I'm not having to worry about this breaking from moving around too much. So this allows me to get into a fairly small space. That's probably about, not quite 2 millimeters, and then the other end is just connected to a BNC jack here, or cable, and this works out pretty well. And I must have done a good job because my wife said the coil was pretty. So in order to use this snooping coil that I just created, because I don't have in 4 hands, I had to create a way to suspend my Ebow over the guitar strings and have it be in a very stable position and not move, so that whatever measurements I take are going to be consistent. So I came up with this creation here, which is just an addition to my Ebow test jig, and that is a way to kind of suspend the Ebow over the guitar strings that allows me to have enough room to stick my snooping coil between the string and the pickup to see what's going on. So this is what I came up with, and it works pretty well. The masking tape basically puts everything in place, and the ribbon is just insurance that nothing goes anywhere. And I had to add this little leg here, which also serves as my place to mount the label for my patented Ebow levitation device. And anyways, I added the leg because it wants to try to fall over because it's too heavy on this side. So I added the little leg that makes it stable, and so now we'll go ahead and see what we can do for learning a little bit more about the input and output coils. Here I have the Ebow levitation device all set up. My do-it-yourself snooping coil is right here, and it's between the string and the Ebow. Right over the pickup, there's about a 5mm gap between the string and the pickup. And so let's turn this on, and we'll go to regular mode first. And we're seeing about 46 millivolts peak to peak, 9 millivolts RMS. Max voltage is about 26 millivolts. I'll go to harmonic mode. And here we have peak to peak voltage of 51 millivolts, RMS voltage is 10 millivolts, and max voltage is 28 millivolts. So you can see there's a little bit of a boost in voltage between harmonic and regular modes. Now I don't know if this is the correct way of interpreting some of this information, but if the input coil is around 565 ohms, then the output coil may be somewhere around 22 to 25 ohms based on the driver coil voltage ratios. Let's take a quick look at the output of the pickup now. This will be normal mode. So our RMS voltage is 1.21 volts. Voltage peak to peak is about 5.5. And let's switch over to harmonic mode. And our voltage here is 1.37 RMS and 6.73 volts peak to peak. So it really drives the heck out of that pickup, doesn't it? In my LM386 schematic that I've been using, I could not get the output to not be some kind of mangled mess that was not anywhere close to half the supply voltage. And what I discovered was that I had accidentally connected these two wires together. And of course, in hindsight, I could see why that totally screwed up all of my simulations, but I didn't notice it until just recently that I had made that mistake. So I'm a little embarrassed that my previous simulations are kind of messed up, but you know, we can move forward from this point here. So kind of the one unanswered question I still have is, what is the purpose of the diode on the regular mode? I can only surmise that maybe it somehow helps to for the circuit to accent one harmonic versus the other. Like maybe it needs to run at a little bit lower voltage, coupled with the fact that the oscillator is running a little bit slower, and that will accent the second harmonic versus the third harmonic when we're going straight to ground, higher power supply by 0.7 volts, and the oscillator is now running a little higher. In normal mode, it appears the operating frequency would be 2.4 kilohertz, and then harmonic mode is 2.6. So it must be some combination of factors like that that causes the harmonic mode to run at the third harmonic and the regular mode to run on the second harmonic. So this does not do what the patent says. The patent says that they're reversing the current in the coil. Maybe that's what their original prototype did, is they actually literally reverse the coil or something, but they found another way to do it that has the same end result. But this is how I interpret it. I don't see how this could be reversing the current. In this final test, we're going to take a look at what's happening across the diode. What I've done here is I've clipped the positive lead to one end of the diode, and I've connected ground to the battery ground. And I'm going to have the scope in AC mode, and I'm going to turn on the circuit. So I'm in harmonic mode here currently. You can see we kind of have a triangular shaped wave. And now I'm going to switch it over to the regular mode. And we'll readjust that. So here we have something interesting. We have what looks like a really clipped sine wave with a very flat bottom and a little bit rounded leading edge on the top. So now let's put it in DC mode and see what that looks like. Pretty much the same thing. And that's what it looks like in DC mode. After quite a bit of fiddling around with LTSpice here to try to model the Ebow circuit as closely as possible to the real world, this is the Ebow circuit as I had mine rebuilt. It's not exactly the same as the actual Ebow. We don't know some of the factors in here, like what are the actual input and driver coil specs and all that stuff. But anyways, the way I found to model this is to make an equivalent circuit of a guitar pickup and then inductively couple it to the output of the driver coil. And then that's when I started seeing waveforms that look very similar to the real world. And in one of my previous videos, this is the output of the Ebow going into an oscilloscope. And I was looking at a open B string, so 247 hertz, which is what I modeled here in LTSpice. And you can see the regular mode. This looks very similar. I mean, it's not exactly the same, but it's pretty darn close. And then if we come over here to the harmonic mode on the right side, you can see that looks pretty darn close too. Now, we don't have the little hump here on the waveform, but I mean, I'd say for a model, virtual model of the circuit, that's pretty darn close, and that's probably going to be as close as we're ever going to get. In this LTSpice model, we can see what the response time would be from when you pluck the string to when the Ebow circuit picks it up and runs with it, so to speak. So here would be the initial response of the string. You can see how it kind of goes from nothing and blooms to a certain voltage. And then at the input, we can see what's going on there. So if we zoom in on this, you can see here that this is the oscillator frequency, right? So it's on standby. You place a metal object between the driver coil and the input coil, and somewhere around 12, 13 milliseconds, it says, hey, there's an object in my view, so to speak. And so the oscillator starts, and then for about like the next 70, 75 milliseconds, the oscillator begins to assume the frequency of the guitar string, and then after, well, in about 1 second, it's up to full speed more or less. So I just thought this was an interesting model. I did not come up with this on my own, but this is using the values of my rebuilt Ebow, and so a fully functional, unmolested factory Ebow should be even performing even better than this. Here I have plugged in the actual values of the components used in the Plus Ebow using estimated specs for the coils and some rough modeling for battery impedance. And now we have gotten even closer to the actual waveforms observed in my earlier videos. Here's what we now know about the Ebow circuit. The circuit is an LC oscillator. The values of the input coil, input capacitor, and the feedback resistor determine the frequency at which it operates. While we have not been able to determine the exact characteristics of the driver and input coils, we have some rough idea of what they probably are or need to be. The circuit is normally in a standby state. When a metal object is placed between the input and the driver coils, the oscillator begins to run through inductive coupling, and the frequency of the guitar string quickly takes over. Once the feedback loop is going, all it has to do is maintain it. Where you place the Ebow in relation to the guitar pickup determines how intense it is. The pickup output voltage can thus dramatically change. The circuit will self-oscillate at a frequency of approximately 2.4 kilohertz in the normal mode and 2.6 kilohertz in the harmonic mode. This is probably the optimal range for the circuit to excite a guitar string into vigorously vibrating in the range of frequencies possible on the guitar. There is a gain boost at 2.5 kilohertz, which is probably why the circuit is utilizing oscillation frequencies of 2.4 and 2.6 kilohertz. The feedback loop, as the patent states, provides positive feedback. This is what enables it to cause a string, which is in a resting state, to begin vibrating very vigorously all on its own. The circuit takes advantage of a certain characteristic of the LM386. The output is always half the supply voltage. This enables a very stable positive feedback loop. The circuit needs to be capable of driving a guitar pickup output to around 1.5 to 2 volts in order for it to maintain enough strength for fretting notes. Too low of an output and the circuit can't put enough energy into the strings to keep the cycle going, as well as upsetting the oscillator. The polarity of the magnets appears to be both north poles facing each other. The exact composition of the magnets is not known, but they do appear to have a Gauss strength of somewhere between 1 and 3. The rings around the windings appear to be steel with some sort of coating on them. They are probably used as shielding and to help direct the energy towards the strings. The purpose of those two round pads under the output capacitor is still undetermined. And last, the circuit board is completely encased in some sort of hard goop. Some people think it might be a 2-part urethane. It smells a bit like gasoline when you pick at it. While it may be easy to come to the conclusion that it's done to prevent people from reverse engineering the Ebow, I believe it serves at least 2 other purposes: circuit stability and the prevention of microphonics. In my testing, I found that it's quite easy to go from a working circuit to one that wasn't. Once verified that the circuit is functioning properly, completely potting it and a substance which entombs the circuit board and which makes it like a brick makes sense from a reliability standpoint. The purpose of the diode appears to be either helping or suppressing the harmonics that find their way to the output coil.